completing the square. Looks like page 405.
Yep.
Yeah, page 405. Those were focused on kind of like the beginning steps of working with completing the square. Less of the application. It was like coming up with a value to complete a square if we didn't know C, for example. So we had a vertex form. We need that for vertex form, right? Gosh, what else do we? If we had the standard form, which this right here, is there another way to write the standard form? If I substitute for C, where does C come from in terms of A and B? If this is going to be a perfect square, where would that come from?
B over 2 squared.
Yeah, B over 2, quantity squared. So it's half of the B value squared. So that will be equal to C if and only if. So I write 2x. If and only if this is a perfect square. So that's kind of like, that's the caveat. When we want to make something into a perfect square, something which is not, we have to consider the b over 2 quantity squared. And once we do that, we have a perfect square. There is nothing wrong with writing, you know, like y minus k is equal to, and then having this side a perfect square. I mean, that's what we want to do. That's the strategy behind all of this.
So it's the b over 2 squared is equal to c if the bx is a perfect square, or if the entire thing?
Yeah, if the entire thing is a perfect square. So in order to have a perfect square, the c value is going to be b over 2 squared. So for example, if you looked at the question that you had to complete, pick one of these numbers here, number 2, which is x squared plus 14x. So x squared plus 14x. I mean, what we're going to put here is going to be b over 2 quantity squared. So in this case here, what we're trying to do is we're saying, well, if this is b, we're going to take 14, we're going to divide it by 2, and we're going to square it. So that ends up being 49. So if we were to add 49 to what was given, x squared plus 14x, that's a perfect square. That can be factored into a binomial squared. So what is the binomial?
X plus 7.
X plus 7.
So then why would you say that equals c if and only if that entire thing is a perfect square, if the b over 2 is what makes it a perfect square?
Well, let's say I had something like this. Is that a perfect square?
No.
No, because this is not equal to 7 squared. So in this case here, you can do two things. You could say, if this is equal, the y equals this, you could go and say, well, I'm going to take this 40, I'm going to put it over here, and then I'm going to add 49, because that's what makes this a perfect square, and I'm going to add 49 to this. Both sides get 49 added to it. So then what you have is you have y plus 9 is equal to x squared plus 14x plus 49. Now we can go make it a circular operation. Subtract 9, you're back to where you started. And all we're doing here is we're manipulating this equation algebraically. And the purpose behind manipulating the equation is to get it into a perfect square form, because we know when we have that our h and our k value become the vertex. So what this does is it allows us to find the max or the min, which is very important when it comes to application. How high is the rocket before it comes back down to Earth? How high is the ball before it comes back down to Earth? How high is the arrow? Things like that. Or how low does something go before it starts increasing? And these applications can be things dealing with money, they can be physical, they can be medicine, they can be any function that we can model with a quadratic lends itself to this type of use, being able to just manipulate the equation so we can see answers more easily. You see, when we're working with quadratics, you know, you might have either one of these situations. When we're working with quadratics like this here, things that are important are the maximum or the minimum. And if there's an x-intercept, that's important. So if we have this right here, a y-intercept might be really important too, because these are all points of interest, because you know, they're maximums, they're minimums, they're places when the equation is evaluated to be equal to 0, or the equation has a beginning value in the case of a y-intercept. So we see this with this model here. And now what we're trying to do is we're trying to take the algebraic model and come up with all of these things. But still relate it back to the equation. Or I'm sorry, relate it back to the graph if you need to. So we're becoming more abstract. And we are trusting what we know can be done to an equation. That's a big step where you guys are at right now, is you've got all the, you know, many of the tools to manipulate equations. Now it's a matter of recognizing what tool you use to get some kind of outcome, desired results. So, we can rewrite in vertex form. That's what those first 7 questions were all about. Did you want to ask anything about those first 7? Look back at them. I know it was a number of days, like a week, but is there anything there that you wanted to ask about? Otherwise, what I will give you is the rest of the homework from this lesson today. But I also want to show you an example or two about how the application of completing the square works. So, shall we go forward? Yeah? Yeah? Yeah. Okay. Then, this goes away. Okay, so they give a ball thrown straight up from a height of 12 feet with an initial velocity of 32 feet per second. They say then the ball's height y after x seconds is given by an equation. So let's just write the equation ourselves with this example with a ball. What's the general form of a projectile? How does this go? Height is equal to what? So think of it as y is equal to. This is one that we want to start cementing in if we can. Do you recall it?
-1/(g)
Times time squared. And g is acceleration due to gravity. Most people will just say it's gravity, but it's an acceleration. So I'm kind of formal about that. Plus the initial velocity multiplied by time plus the initial height. mark this as something to refer back to. So this goes into your repertoire of formulas, sort of like area of a circle is pi r squared. This is going to become more of a reality now that you have quadratic skills. Okay, so
So V is velocity?
yeah, this is I gave you this the other day. That's initial velocity. Speed. G is acceleration, gravitational acceleration. And when we do G, remember, is going to be 9.8 meters per second, or 32 feet per second. So that right there, if you have that information, you can handle any of these projectile type problems. So, what's the initial velocity of this ball? 32 feet per second?
Yep.
So now we know we're working in feet per second. So then G is going to be 32 times a negative half. So that's going to become negative 16. And then what's the height that the ball is thrown from?
12 feet.
12 feet. Okay. So we had a quiz problem where we had to plug in some initial velocities, and I think it was King Kong throwing Lois Lane or whoever it is, I can't remember that movie. So throwing something off of the Empire State Building at 1,250 feet. I'll give you those back in a bit here. But this right here, we are supposed to do what? They say, rewrite the formula in vertex form, and then find the maximum height. So in other words, we're finding the vertex of this. That's the whole purpose. So in order to find the vertex of this, somehow or another we have to turn it into a perfect square. Now, like I showed you before with that problem that had 49, it started out with x squared plus 14x plus 40, and then I took away the 40 and added back the 49. We can take away the 12 and move it over here, or we can just think to ourselves, what do we want to do to this in order to turn it into a perfect square? And this is complicated because it's a negative 16t squared. So factoring this one is not real easy, so we have to pull out a couple of tricks. I think what we should do is this. I think it's best right now to add a negative 12 to both sides, and then figure out what we have to add to the whole equation in order to make it into a perfect square. So what do they go and give it being done with a CAS? Sure enough, that's nasty. They go and they do this one with a CAS.
So we do half of 32 and then square.
Yeah, you do half of 32 and you square it, but that's going to be a big, huge, ugly number, isn't it? So here's what I want to do first. Show you a little bit of a trick that we can do. We can change this to begin with. And the way we can change it is by factoring out a common factor from the 16t squared and the 32t. So what could we factor out of this?
8.
8 works. Can we go bigger?
Can't we go 16?
You can go 16. And what's really sweet is if you can take a negative 16. So then negative 16 times t squared minus 2t. Now, can we go further than that even? You could. You could pull t out if you needed
Yeah,
to.
could you do 16t?
You could. You could pull out a 16t. But in terms of being able to work with this, what I'd like to do is I'd like to try to rewrite this as a quadratic. So then what we can do is we can come up with what the vertex is going to be more easily. So if we just take a look at this portion, what do we have to add here? Now this is important to keep track of your numbers. What do we have to add here to make this into a perfect square in the parentheses? Half of negative 2, and then we square it. So half of negative 2 is negative 1, and you square it, and that's equal to 1.
Wait, but wouldn't it be, so if it's b over 2 squared, if b is 2, so then,
B is negative 2. Because this is, if we wrote it in standard form, it would be plus and negative 2.
so then why would 1 be positive?
Because if you,
Oh,
negative 1 half quantity squared, or,
right,
sorry,
okay.
negative 2 halves quantity squared is negative 1 times negative 1, which is
Oh.
1.
I
Okay,
forgot
now-
about squaring it.
So we added 1 here, right?
So I have to do it to the other.
What do you think you do to the other side?
Subtract 1. Well, because if we had it, no, if we had it before as the y minus k, and when we put the k on the other side, it turned into negative, so wouldn't we have to do that back?
If I add 1 on this side of the balance, what do I add on this side of the balance to keep it equal?
Well, I mean, you would add 1 if you say it that way.
Good, that's what we're doing, because there's an equal sign there.
But I thought we were doing the whole, like, y minus k thing.
We are. So what we did is we subtracted 12, we brought it over here. Now this is y minus k form.
Uh-huh.
Then I added 1 to that side of the equation. So I have to add back to this side of the equation the same amount.
Oh, so we're not, okay, I thought we were trying to get rid of the 1 on that side.
No, we're leaving it, we're adding it in. But now I want you to settle back into looking at this and ask me, what do you add on this side?
Is it the 1 times the negative 16?
Yes, it's 1 times the negative 16. So if I added 1 times negative 16 over here, I have to add the same thing to the other side. That's the thing about factoring out this, is you gotta be careful what you're adding. Okay, so I just want to take a look at what the book is doing to make sure that we're not making it a whole lot different. There. They got 12, they have negative 12. They're doing it a little bit differently. Okay, well, let's keep on chugging along. Okay, now, what is the left-hand side of the equation? H minus 28. Okay, and that is going to be equal to. So now what we should do is we should write this in vertex form, which is y minus k is equal to a times x minus h quantity squared. So now we have a negative 16 because that's our a value. And then what we're going to do is we have to come up with the binomial square that this quadratic is equal to.
T plus 1. No, T
So
minus.
is this t plus 1 or minus 1?
Minus.
So
we have
minus 1 squared. So now you have it in vertex form. So what is the vertex? 128. So HK is 128. So after 1 second, this thing's at 28 feet. That's the whole problem. So the steps that we followed are taking the original equation and writing it in vertex form. That was step 1. And then interpreting vertex form for your answer. Step 1 was a lot more complicated though, because these quadratics are not easy. Because we have to clean them up. Now yes, you could have left it just like this here. You could have subtracted 12 from both sides. You could take a half of 16, or a half of 32, which is 16. It's squared, and you could add it to both sides. And then you could go and you could factor this whole thing. And you would get exactly the same thing. So why did we take the negative 16 out in front? It was to make the factoring easier. You see, if we'd have gone the long route here, negative 16 t squared plus 32t, and then if we subtracted 12 from both sides, here's what we have to do. We've got to take 16 squared. What's 16 squared? $256. And then you look at this and you say, hey, now I got to factor it. And if you don't use pulling out a common factor, factoring that ends up being a challenge, because what you're going to have is you're going to have a negative 4t plus something, and then you're going to have 4t plus something, and it gets really big with numbers. So the trick to that, even if you got yourself here, you guys, if you ever get yourself in that situation, look at this and say, well, hey, at least they're even numbers. So we could factor out a 2. And then you start looking closer and closer, you'll eventually see that you could factor out a 16. And if you made it a negative 16, then you would be, and this is 16, right?
Would it have to be negative 16 to get a positive 256?
It would have to be a negative 16. Is that right? So do I have it all coming out correctly now? Yes. And I'm feeling like this is not necessarily, this ends up being a negative 16 times. Is this factorable? It's not. So you'd have to use the quadratic. No, I don't want to go there. So, factor early. Quadratic is Friday. So we'll wait till Friday. So there you go. That's the kind of application that there is.